Okay, hello guys, welcome back. And just like I said in the last video, I'll be taking another example on the constant pressure process. We took the first example, so we are taking another one now. So, example 2, a mass of 0.2 kg of air at a temperature of 165 degrees Celsius expands reversibly at a constant pressure of 7 bar until the volume is doubled. Find the final temperature, work, and the heat transfer. So, as usual, we start by bringing out our parameters. So, parameters given, we have that this is my parameters given self. Okay, parameters given. Okay, yes, neatly ruled. We have our mass 0.2 kg. So the first temperature we have here is 165 degrees C, which is equal to 438 Kelvin. Okay, now at constant pressure means P1 is equal to P2 is equal to 7 bar. Now V2 is equal to 2V1, since they said the volume is doubled. So the first volume is V1 and the second volume is double of the first volume, but the first volume is unknown, so 2V1 is V2. So now we go down to our formula. So before that, our ideal equation, the ideal gas equation, which is P1V1 over T1 is equal to P2 V2 over T2. So if P1 is equal to P2, which is equal to P cancels out, we're left with V1 over T1, which is equal to V2 over T2. And from our past knowledge, our secondary school knowledge, this is Charles' law. Okay, yes, this is a Charles' law, where the volume varies directly proportional as the temperature. So we have this to be this. So finally, T2 is T1 times V2 all over V1. So we have our T1 as 438 times, what is V2? V2 is 2V1 all over V1. V1 cancels V1. Okay, we're left with 2 times 438 Kelvin, which is, what do we have? 876 Kelvin. Alright, so I haven't done this. We'll see. Okay, from the first law, heat transfer plus work is equal to U2 minus U1. Alright, but work is equal to what? P change in V, which is equal to what? MR change in T. Okay, now our work remains W is equal to minus P what? change in V, that is the V. So finally this should give us V1 minus V2. Okay, V1 minus V2. Alright, yes, so that work done will be equal to do we have volume? No, we don't have volume. All we have here is the temperatures. So we can say, using this, since it's an ideal gas, this is for when we use steam. Okay, for the steam, let's not use this. For the ideal gas, use this. Okay, so work done will now be, we have our mass 0.2 times the value of R is 0.287. Okay, it's in kilojoules per kilogram Kelvin. T2, we got our T2 as 876. We got our T2 as 876. So I'm going to clean this and write T2 that we got minus 438. Okay, so finally work done will be equal to 25.14 kilojoule. We have gotten our work. Remember from our proof in the last episode, in the last video, that Q is equal to H2 minus H1, that is for steam, and also we derived that Q is equal to MCP T2 minus T1. Alright, so having done this, we can say that 0.2 times the value of CP is 1.005 kilojoules per kilogram Kelvin into 876 minus 438. So finally heat transfer, our heat transfer is 88.03 kilojoules. So we have gotten our final temperature T2. So you can come here and say 1, the final temperature, then our work done, which was the second question, then finally our heat, which is the third question. So this ends the question, and we solved it. As you can see, it's not difficult. It's all about knowing the convention, knowing when to use the formula at constant pressure and at constant volume, and so on and so forth. So having said this, we have come to the end of this particular episode called the non-flow process at constant pressure, or the constant pressure process, which is also known as the isobaric process. So stay tuned. In the next video, we'll be talking about the isothermal process, which is the constant temperature process. So stay tuned and have a great day. Bye.
It leads to liquor on some ladies. Yeah, we did turn up on a daily. It's how I walk up. Yeah, soft walk.